Welcome to our discussion on inequalities. Here are the objectives for this video. You can see that we're just going to look at two different types of inequalities, polynomial and rational, and they're really pretty much the same technique. They only involve a slight deviation from each other. So let's start with our polynomial inequalities. So the nice thing that we found out earlier from the intermediate value theorem is that we know polynomials, the function, as long as it's a polynomial function, it's a nice smooth curve. And so that function cannot change sign between each successive zero. So every time it crosses the x-axis, it can't go from being positive to negative without crossing the x-axis again, right? And it can't go from negative to positive without crossing the x-axis again. So we know that in between any two successive means just one after the other. So any two zeros of a polynomial, that polynomial has to always be positive or always be negative in that interval. That's going to help us a lot when we're trying to determine when polynomials are greater than 0 or less than 0, i.e. when we have inequalities. Because if we know where it's equal to 0, right, if we have these zeros, if we found these four critical values, then we know that in between them, it has to maintain its sign, right? It has to always be negative or always be positive in between successive zeros. So that's going to help us be able to determine where our polynomials are greater than or less than 0. Here are the basic steps. The first thing we have to do is basically solve our polynomial for 0, right? So we have to move everything onto one side, because a lot of times with inequalities, it'll have kind of a polynomial set greater than or equal to another polynomial. So you'll want to move all that junk onto one side and have it greater than or equal to 0. Or move it to the other side and have it less than or equal to 0. It doesn't matter, right? Move it all to one side so that you have just 0 and just a polynomial on the other side. And then factor that resulting polynomial the way that you always factor polynomials, right? We have our simple three steps. We do our P's and Q's. We guess and check. We find our things. If we get it down to a quadratic, we use the quadratic formula or we factor it. And we basically reduce it all the way down to as irreducible as it will go. Sometimes, some polynomials, remember, will not reduce down beyond a quadratic. And if you get to an irreducible quadratic, something like, x squared plus 4, where the only solutions to that are complex, just remember that we're now back in the quote-unquote real world. We're only working with real numbers. So you're not looking for complex solutions anymore. You're only looking for real solutions, things that you can plot on the number line only, right? So we're only looking for real zeros, things that can be plotted on the number line. Okay, once you have found all the zeros, what you want to do is you want to plot them on the number line. So just draw yourself a simple number line and put little dots where all your zeros are. Don't worry about making them to scale, right? Just put them in order. Make sure that the smallest one is, furthest to the left and the biggest one is furthest to the right. Give yourself a little space in between them and you're good to go. That's all you have to do. Now, this whole making the table thing, it's nice and it's helpful, and I'm going to show you what I mean by that. And you probably want to do it a few times until you get comfortable with the technique. But the whole point of making the table is just helping you decide which interval satisfies your inequality or not. So after you get better at this, you don't have to spend the time making a table. You're still just going to pick test points and figure out which intervals work and which intervals don't. And I'll point that out as we go. All right, so let's look at a simple example. Say we've got a polynomial on the left, a polynomial on the right. I mean, it's really technically a monomial because it's only got one term, but you get the idea. We need to get it all on one side, so it's going to be easier to move the 13x over and have 0 on the right. If we had a linear x over here, right, if we had like a plus 2x on the left-hand side, we'd want to combine them, obviously. You want to clean it all up, make it just one normal polynomial, and then factor like you normally do, right? So use your P's and Q's, right? Remember, factors of x divided by factors of 2. Then try it with synthetic or long division, whatever you do, and figure out what those zeros are. And we found the zeros of -3, 1/2, and 2. So the next thing I always suggest is put those on the number line just so you can kind of visualize what's going on, right? That you don't have to write out these intervals like I have here. This is, I think it's better just to go, okay, I've got a point here, I've got a point here, and I've got a point here. And you'll notice that I'm not really worried about spacing. I just know that, right, this is -3, this is 1/2, and this is 2. And I'm concerned with what's happening in each of those intervals. So we go here. Again, here's my number line, right? Here's my points on the number line. You can have a table. This really helps, especially in the beginning, but once you get better, you don't have to worry about this. So here are all my factors. All we're going to do now is we're going to pick a test point. So in each interval, we're going to pick a point that's somewhere in this interval. And you obviously want to pick easy points. So for instance, in this interval here, between a negative and a positive number, the easiest point to always pick is, and hopefully you're all screaming at me right now, 0, dummy. Yes, 0, right? You pick 0 because that's the easiest thing to plug in. Because all you're doing is you're plugging that test point into each of your factors, and you're asking yourself, is the result positive or negative? You don't care what the number is. You just care if it's positive or negative, right? All right, so let's look at some simple test points. This one, let's pick -4. Obviously here we want to pick 0. Between 1/2 and 2, we obviously want to pick 1. And then 3. Nice and simple, right? Put a -4 into this factor. You get -4 minus 2. That's a negative number, right? Put -4 in here. You get -8 minus 1. That's also a negative number. -4 in here. -4 plus 3. That's a negative number, right? A negative times a negative gets positive times a negative. The whole thing is negative. Repeat the process. Plug in 0. 0 minus 2, negative, right? This goes away, -1. This goes away, +3. The whole thing is positive. Repeat the process 2 more times. We'll see that in the first interval, it's negative, then it goes positive, then it goes negative, then it goes positive. So this one alternates, guys. It doesn't always alternate. So be careful. Don't just pick one and move on, because you could have a function that does this, right? It goes up, down, comes up here, touches, and then goes back down, right? So you'd have a 0 here, a 0 here, and a 0 here. So you'd go negative, positive, negative, negative, right? So it doesn't always have to alternate. So you have to check every single interval to figure out what's going on. It's just going to be a lot of the examples you see will alternate, but don't get caught thinking that it always alternates. Okay, so we can check the endpoints. And when we mean by endpoints, it's because if you'll remember, the original inequality that we're dealing with wasn't a strictly greater than, it was a greater than or equal to. So by checking endpoints, we just want to see which ones actually satisfy it as far as make it equal to 0. So when we check our endpoints, we see that when we plug in -3, it equals 0. We plug in 1/2, it equals 0. We plug in 2, it equals 0. And it's kind of like no duh, because those are zeros, right? Duh. So we know that all of those endpoints get square brackets. Of course, infinity always gets a round bracket. And if it was negative infinity, it'd be the same thing. And so those are the intervals that satisfy that inequality. Simple, easy, guys, right? So put everything on one side, set it equal to 0. Factor it to find your zeros using the techniques that we've already learned. Plot those zeros on the number line, and then pick test points in each of those intervals, plugging them into your factors to determine the sign of them, then figure out the overall sign of the entire polynomial, and just see which intervals satisfy the question, right? If the original question is less than or equal to 0, then you're looking for where the overall polynomial is negative, and of course, if it's greater than or equal to, you're looking for where it's positive. Simple, simple, simple. Okay. Rational inequalities, really no different. The only difference with rational inequalities is that we have a fraction. Now, when we have a fraction, right, we have a polynomial over a polynomial, we have to worry about when the polynomial equals 0 and when the polynomial is undefined. So basically, we worry about when the top is 0 and when the bottom is 0. And we just call these cut points. Sometimes they're called critical points. We're basically just looking for when either of the two pieces are equal to 0. Okay, so whether you hear someone talk about them as being cut points or critical points, it's the same darn thing. I tend to use critical points, but I put cut points in there as well because people tend to use that a lot. Okay, so if we look at this function, this example, we can see that the top is equal to 0 at 2, the bottom is equal to 0 at 4 and -3. So there are our 3 critical points, cut points, right? And we can see that the function remains one sign in between, right? So to the left of this one, it's always negative. In between these two, it's always positive. In between these two, it's always negative. And to the right of that one, it's always positive. So just like the polynomial functions, they follow the same rules, that they're always going to be one answer in between these critical points, these cut points, right? In between your quote-unquote zeros. So nothing has really changed. In fact, if we look at our steps for doing these, we can see that they're exactly the same as well. So you can see the first step is still the same. We move everything onto one side so we can get our inequality set, equal to 0, or less than or equal to, greater than, whatever. So we have 0 on one side and everything else on the other. The only difference now is instead of combining all that stuff and having one nice polynomial, we have to combine all of our stuff to make it one rational function. We have to make it one fraction, which means finding a common denominator. Once we have that, we factor the numerator and denominator to find all those zeros, which is the same thing we did with a polynomial, right? We had to factor it to find all of its zeros. Then we have to find the intervals, which is the same thing we did before, i.e. plot those zeros on the number line and figure out, where the gaps are. And then, same thing, make the table if you still need to, but plug in your test points, figure out which things work, which things don't. Check your endpoints. Remember, if they're inequalities, we're looking for sometimes they can equal 0, and if it's strict greater than or less than, then we don't have to worry about it. Everything's round. Let's look at an example. First step, put everything on one side, so you bring the -1 over, so now we have a 0 there. Yay, everything's perfect. But now we have to turn this whole thing into one big fraction, right? Before we had to turn it into one big polynomial, now we have to turn this one into one big rational function, i.e. one big fraction. So, common denominator. So that -1 just became the bottom polynomial over itself, right? X squared minus 2x minus 3 all over this thing. And so we combined it to have the top of the first one minus this new -1 top, right? All over the same thing. We combine like terms, we clean everything up, and the top just becomes 4 minus x cubed. Now that we've got one big fraction, just like before when we had one big polynomial, we factor. So we factor the top, we factor the bottom using the same techniques we've learned. So there's the top factored, there's the bottom factored. We find the zeros of everything. Zeros at the top, zeros at the bottom. Give us 2 and -2 on the top. Give us 3 and -1 on the bottom. Then, just like before, we find those intervals, but really, more importantly, I think it's better to draw the number line and put them all in, right? So here's -2, -1, 2, and 3. Again, we don't care about scale. We just want to space them out so we can find some test values. So we're going to come along, excuse me, and in each interval, this would be -3. A number in between these two is tough, right? Because they're consecutive integers. So we can't pick a nice integer value. So we have to pick -1.5, 1.5. In between these, though, we can pick 0, which is always nice. And then again, in between these, we're kind of, we got to pick 2.5. And then out here, we can pick 4. So those are going to be our test values. So again, here's our interval. We take our test values. We plug in -3. So 2 minus a -3 becomes plus, right? 2 minus 3 is negative. -3 minus 3, right? -3 plus 1. So when you put them all together, you get on the top positive times negative, which gives me negative. On the bottom, we get negative times negative, which is positive. We get negative divided by positive gives me negative, right? So we repeat the process. So even with the -1.5, 2 minus a -1.5, well, just becomes plus, so that just becomes positive. Forget it, move on. 2 plus -1.5, so you're basically 2 minus 1.5, but that 1.5 is smaller, right? So that's still positive. -1.5 minus something else, that's a negative. -1.5 plus 1, that's a negative, right? So it's not so bad even when you have decimals. Repeat the process over and over and over again. We can see that here are all of the places where it's greater than, because if you remember, our original thing was we had our fraction greater than or equal to 0, and it was a greater than or equal to 0, right? So we have to check our endpoints. With -2, that makes the top 0, so that one's fine. With -1, that makes the bottom 0, so that's no good, right? We can never divide by 0. So we're going to have a square bracket here and a round bracket here, union. And then 2 makes the top 0, that's fine, square bracket. 3 makes the bottom 0, that's no good, right? So that's going to be our interval. On the next slide, we can see the picture. There's the interval. Here's the picture, right? So whether it's a polynomial or a rational function and you're doing inequalities, the steps are basically the same. Put everything on one side, simplify it up. If it's a polynomial, you want to simplify it into one polynomial. If it's a rational function, you got to simplify it into one rational function, i.e. find a common denominator and make it one fraction. Once you have it simplified, you factor it to find all of its zeros. Once you have all of its zeros, you plot those on the number line to see what your intervals are. Once you have your intervals, you take test points, right? You just pick a value in each of your intervals, obviously picking the easiest ones you can. Take those test points, plug them into all of your factors, determine if the overall function is positive or negative, which then tells you on which intervals it satisfies your inequality. Then you check your endpoints to see which ones you can allow to equal 0, and you're done. All right, guys, go practice.